Okay, so this lecture is another example of how to do an impedance, how to use an impedance method for finding a transfer function. And in this one, we're going to use a couple tricks that I haven't shown you in tandem yet, so I want to show you them. This is very similar to one of your homework problems, but it's tweaked. So, in the circuit shown, what is the transfer function from the voltage source to the current through the resistor? Okay, so that's the problem statement. I'm just going to talk for a minute about our overall strategy here. We could use the sort of general method from 13.4 in the textbook, and that is totally fine. However, I'm going to use this is a problem that doesn't have an immediate application of the across or through variable divider rule, and yet it can be arranged to be that. So that's the method I'm going to use still. I'm going to use it to apply to this problem, which is admittedly it's probably not any better than using the general method. I just want to show you that this method does work for problems it's not immediately obvious to apply to. So the strategy we're going to take is to rewrite this left-hand loop of the circuit to be an equivalent voltage source. Okay, and then if we connect that equivalent voltage source, which will absorb that capacitor into it, then it will be an equivalent voltage source, an equivalent impedance in series with L2 and R, which will allow us to use the voltage divider rule to write the transfer function from Vs to Vr. However, we would like the transfer function from Vs to Ir, which is closely related just through the impedance of R. So we'll be able to do that in sort of the last step pretty easily. So we're going to go after Vr over Vs, that transfer function first, and using the voltage divider rule, and then we'll, in the last step, we'll convert it to IR. Okay. So the first step is actually the trickiest, probably, and that is finding an equivalent source model. So you could write any part of the circuit as an equivalent source, but we're choosing to write this part of it as the equivalent source. So we're going to imagine that these terminals here, they will just sort of stick in there. These green terminals are going to be the output of this circuit, and that will be the input to this latter half. So we should be able to write the left-hand loop as an equivalent circuit, a Thevenin equivalent, and that's going to make our graph, well, we haven't even really drawn a graph yet, but we'll draw the circuit with an equivalent source. So plus minus VE, the equivalent source, is going to be in series with, well, I'm actually not going to put, we don't want to draw a resistor there. We want to draw just a general impedance, ZE, in series with L2 and that is in series with R. Oops. So R, and this is our output. So once we have VE and ZE, we can use the across variable divider rule. We don't even really have to draw a linear graph for the case of a circuit because it's already connected like a circuit, we can, if you guys wish. It's not a big deal either way. So our goal, though, is to find out what is VE and what is ZE. So let's find ZE first. So this is 1A. This is the output impedance of that left-hand loop. So the output impedance is always going to be the impedance of or between these two terminals when all the sources are set to 0. Okay, when the voltage source is set to 0, that means there's no potential difference across it, which means it's acting as a wire. So we short it out to 0 it. And we have, between these two nodes, we have two paths. So we have the path through C and we have the path through L1, which means that they're in parallel with each other. And the equivalent impedance ZE is then either the 1 over 1 over formula for equivalent impedance, or it's just ZL1 ZC divided by ZL2 ZC. Oh, plus. There was a plus there. Otherwise, it'd be pretty trivial. Okay. And, sorry, I don't know why I wrote 2. That was ZL1 ZC divided by ZL1 plus ZC. For some reason, that was difficult to write. Let's go ahead and plug in what the impedances are of each of these elements. So the impedance of an inductor is the inductance times S. Impedance of a capacitor is 1 over CS. So let's plug those in. In the numerator, we have LS times 1 over CS divided by LS plus 1 over CS. The S is canceled in the numerator, and let's multiply the numerator and the denominator by S once again, because we have this S in the denominator down here. So that gives us, and we'll drop the L, well, the L over C, we'll leave that for now. So we'll do L over C up here. I don't want to do too many steps at once. Cancel the S's. L times, we wanted to multiply numerator and denominator by S. Sorry, so L over C is the coefficient of S. I want to make sure that that's clear. And we have L S squared plus 1 over C. Okay. I think that can get a little simpler. Let's rewrite it again. Let's drop the let's just drop the C from the numerator down to the denominator and cancel it out. So that's not too bad. So we just have LS divided by LC S squared plus 1. Right? So that is our equivalent impedance for ZE. Okay, now we need to get VE. So this is the equivalent voltage. And that is going to be whatever these output terminals of the left-hand side circuit would be if we had an open, if we had these terminals open, so none of this was connected at all. So that's the question. What is the voltage here. And there's a very reasonable parameter that we have for that, and it's just the voltage across the capacitor is whatever that voltage is. If we look at this circuit, what we have is a little voltage divider circuit. This loop, I should say, this source loop that we're working with. So there's a voltage divider and a cross variable divider here. So we can simply say that VC equals VE equals, and we have so it's going to be the impedance. So this is ratio of impedances first, and that is going to be ZC, the impedance of the element we want the voltage across, divided by ZC plus ZL1 times VS. That's what VE is. And we could simplify that. We can't simplify the VS, but we can simplify the ZC and ZL1. So we have 1 over CS in the numerator. Let's drop the CS down. So we have 1 over, the CS's cancel, 1 plus, and then now we have CS. So there's already an L1 here, C, and there was already an S squared. So that is our impedance times VS. So that is that relationship. Just double check. 1 over CS, 1 over CS, LS, L1S, L, yeah, okay, good. So that is our VE. So not too bad, actually, to find that. So now we can apply our across variable divider to the whole circuit now. So now we have this situation. We found VE and ZE. And we can use the across variable divider again. In a sense, we used it to find the equivalent voltage, but we're going to use it now for the whole circuit. So the across variable divider says that VR divided by VE is equal to the impedance of R divided by the impedance of R plus the impedance of L2, ZL2, plus ZE. Okay, and let's go ahead and plug that in. ZR is just R plus L2S plus ZE, which Z is this expression here, so LS divided by LCS squared plus 1. So let's multiply numerator and denominator by LCS squared. And we're going to have R times LCS squared plus 1 divided by, we're going to have R LCS squared plus R, because of the 1, plus, oh, this isn't, no, that's just any L, right? All of these L's up here are L1. Drop my subscript. Okay. And so now our, so R This is an L. Got to keep track here now. So now I plugged in Z. So these are all L1, L1. And so these are L1 and L1. Good. So now we have L2S times L1 C S squared plus 1. So we have L1, L2 C S cubed, right, plus L2S times 1. Okay, whew, getting pretty nasty. All right, let's just rearrange this denominator. We're almost there. Let's rearrange this denominator now so that it is a polynomial in descending order in the denominator. So we'll do R L1 CS squared plus R in the numerator divided by, and then the S cubed term is L1 L2 C S cubed plus, we have an S squared here, so there's an R L1 C S squared term, and then there's plus an L2S term, L2S term, and then there's a plus R. All right. So that is our expression for that. So the final step then is to remember we have VR over VE, but what we want is actually, well, there's a couple of final steps. Sorry, 2 final steps. First thing is we need to change this VE into a VS. And we can do that with this going back through the equivalent voltage relationship. We see that VE is just equal to this times VS, right? And so, in a twist of fate, we just distributed out this 1 plus L1C S squared term. We're going to multiply it back through again. So this is what happens when you do a problem without having already done it. Doing it live here. So let's plug in our VE as this expression so that it has VS. Notice that that's just going to leave this 1 over 1 plus L1C S squared term in the denominator, so we need to multiply both sides by that term to get rid of it. And that means that we can write that so step 3, use equivalent voltage expression to write in terms of the original source of VS. So that's what we're doing with this step. So we have VR over, it's VE, but we're plugged in this term, so we're going to say VS, and we're going to multiply both sides by this, so it cancels out on this left-hand side. And we get R L1 C S squared plus R divided by, now we plug in this guy, 1 plus L1 C S squared times this whole thing. So we've got L1 L2 C S cubed plus R L1 C S squared plus L2 S plus R. Okay. So that is our it's a transfer function. We didn't distribute this, although we probably should distribute it. I'm going to leave it undistributed at this point. It's going to be pretty nasty, though. It's going to get up to a fifth order polynomial. Which I didn't expect. I expected a second order polynomial, or sorry, a third order polynomial. I'm just going to review this for just a moment to make sure I haven't gone astray. Yeah, well, I clearly have. I think it was I dropped this term here. And I think that now that we know that this L1C S squared term is going to come into the denominator, let's do this. So let's back up to this step here, and let's look at it again. Let's say, so we know we're going to end up with this coming in and knocking a bunch of things out of our way anyways. Let's go ahead and do this step here. Let's do it correctly, though, where I had these two terms, but I forgot the last term, which was plus L1S, which makes this term L1 plus L2S. Okay. And then instead of doing this where we distribute out the R, let's keep it factored here. So we have that. Okay. So if we have that, then when we bring our term over here, and actually, so it was almost correct. We just have an L1 plus L2 that propagated here. L1 plus L2 times S. Then this, if we hadn't distributed it and we had just copied that version instead, we could refactor the R out, whichever way you would like to cut it. It's this divided by that. You can see that this term here and this term here cancel, and you do in fact get third order R over L1 L2 C S cubed plus R L1 C S squared plus L1 plus L2 S plus R. Whew. All right. Whew. So we are almost there. Last step for real this time, is to rewrite this in terms of IR instead of VR. So rewrite the output element, which is R, in terms of current instead of in terms of voltage. So we want the current of R, not the voltage across R, which in an electrical circuit is just related by the resistance, of course. For any old element there, we could just use the impedance of that element, which is the resistance in the case of the resistor. So we know that we'll use capitals here. VR is equal to IR times R. Okay. And so we can just insert this, and there's an extra R there, but we can divide it by the other side. And notice there's an R there, so we get to cancel. It all works out hunky-dory. So we end up with IR divided by VS equals, I'm suppressing the of S notation, equals, and it's going to be a big fraction, and the R's cancel, and you get 1 over L1 L2 CS cubed plus R L1 CS squared plus L1 plus L2 S plus R. Alright, so I think that's right. I mean, this was doing it on the fly, which is not advisable, but hopefully if I made any mistakes, you guys can catch me on that, and I'll fix them. So that is it for that lecture. I just wanted to do another example where I used impedance methods to derive the transfer function. And we did that. If you look back up here, we needed to find a current on the output, and we had a voltage input, so that was a little bit different. We also used this equivalent source trick to get ourselves a nice cross-variable divider rule usage, which was nice. So it all kind of worked out pretty well. Not a ton of algebra. If you did this the other way, with a third-order system, you would be solving a pretty decent-sized set of equations simultaneously. So I like this way a little bit better, so I keep kind of teaching it this way. But the textbook has the other general way. All you're doing is the equations. You could write all your equations down that you need, and you're just solving for the variable that you want. So it's pretty much 6 or half a dozen. This method to me is a little bit quicker and less painful than the other one. The other one, I always want to use Mathematica or something to handle all the variables and get the algebra right. This one, maybe I should have done that, but I wanted to show you by hand how to do it. And it's a little bit easier by hand to do, I think, than the other method is, which is more systematic. You can teach your computer to do it. This one is more intuitive, and, well, it is to me, and I believe it can be for you as well. So that is all. Oh, I did want to mention, we should be able to check here our units at least, right? So if you look at this last term, it's a resistance. We know that has units of ohms, right? It is a whole sum in the denominator. They all should have units ohms, which we could check as well. Would be another good check. But I'm going to say the right-hand side of this equation must have units 1 over ohms. we have a current divided by a voltage, right? And from Ohm's law, we know that voltage is equal to the resistance times the current, and so the unit of current, amps, divided by unit of voltage, volts, V, is just 1 over ohms. So that works out, that checks. So we're at least that right. We also didn't lose any orders in our polynomial, which is a good sign. I would not expect this to be an unstable system inherently for any choice of parameter. So yeah, this all makes sense. So yeah, in any case, let me know if you have any questions. That was just another example for you.